Hello everyone, welcome to our presentation. I am Zirui Wang. This presentation is about our ECCV 2024 paper, CrossScore. This is a joint work with Wenjing Bian and Victor Prisacario. In this work, we are interested in evaluating the quality of a query image. Specifically, our goal is to evaluate the query image by comparing it with multiple views of the same scene, eliminating the need for a pre-aligned ground truth image. We term this process as cross-referencing image quality assessment, and the results as CrossScore. Now we move into the background and motivation section. Basically, why do we need a new image quality assessment method? First, let's look into a popular application these days, which is called novel view synthesis. Given a set of captured images, we can train a neural network such as Gaussian splatting or NERF to enable novel view synthesis applications. After training, we can render novel views from the system and get basically unlimited views of the same scene. We illustrate this process here. On the left, we have a set of captured images represented by gray squares, and on the right, we have a number of novel views represented by a number of blue squares. Here, we would like to highlight that our goal is to evaluate those novel views. Unfortunately, those novel view images usually do not come with ground truth images. While ground truth images are not always available, we still would like to evaluate this novel view system and the rendered novel views. The current approach to do this is to split and subsample the captured images to training views and test views. For example, we might have 100 images and we might take 10% of them as test views. Now the process becomes we train the novel view synthesis system with training views, and we render test views, and we compare those rendered test views with ground truth test views. However, this subsampling-based evaluation is only an approximation. The subsample test views can only provide limited coverage. For example, if we have 100 images and we take 10 of them as test views, so all we have to evaluate this scene is those 10 test views. And in contrast, during novel view synthesis stage, we can render hundreds, thousands of novel views. This is the first limitation of the current evaluation pipeline. The second limitation is about evaluating sparse view novel view synthesis system. Let's take a look at an extreme example. Say if we have 3 captured images in total, and if we follow the current evaluation pipeline, we need to take at least 1 image as test view and 2 images for training view. If we train a sparse view novel view synthesis system in this setup, we might end up with 2 issues. The first one is training sparse view novel view synthesis is already a challenging task. We would like to use as many training images as possible. So in this case, the best scenario is we would like to train the scene with 3 captured images. However, reducing 3 training views to 2 training views might result in a significant performance drop for novel view synthesis system in this sparse setup. The second issue in this process is that we end up with only 1 image as our test view, which at most of the time could only provide very limited coverage and statistic relevance in evaluating the sparse novel view synthesis pipeline. Now, we just mentioned 2 limitations in the existing evaluation pipeline. With these 2 limitations in the existing approach, we would like to propose a new image evaluation method, which is based on multi-view reasoning. Recall that our goal is to evaluate novel views that do not have ground truth in a novel view synthesis application. We then propose a novel image evaluation method for this goal. Specifically, given a query image that is rendered from a novel view synthesis system, our method evaluates the query image by referencing a number of images that are captured for the same scene, but captured at different viewpoints. We name this method as a cross-referencing image evaluation method. We use a neural network for this image evaluation method. Our neural network consists of 3 major modules. The first one is image encoder. In our case, we take a pre-trained DynoV2 as our backbone. This image encoder is applied to both query images and reference images. After extracting image features for both query image and reference images, we apply a cross-attention between the query image and the reference images. After the cross-attention, we apply a shallow neural network to regress an image score map for the query image. We name the result as CrossScore. Now we have our neural network architecture in place. The remaining question becomes, how do we actually supervise this neural network? We propose a self-supervised method via a data engine. We consider to take advantage of existing novel view synthesis systems as our data engine. Specifically, given a set of training images, we can train a novel view synthesis system, for example, NERF or Gaussian splatting. At the beginning of the training of those novel view synthesis systems, they tend to produce images at lower quality, and while training or at the end of the training, they tend to provide high quality images. So we take advantage of this property and we collect a number of checkpoints during the training process. For example, here we show an example that we collect a checkpoint every 1,000 iteration, and we render images from all available viewpoints. For those renderings, because we know ground truth images for this renderings, we can compute common use metrics such as PSNR or SSM, and we use these score maps to supervise our image evaluation network. In our implementation, we use SSM as our ground truth. Here we visualize the SSM maps for query images that are obtained at different checkpoints. With this data engine, we are able to collect a limited number of images with various degree of artifacts and their ground truth SSM maps. We then use those images with artifacts and their corresponding SSM maps to train our image quality assessment network in a self-supervised manner. Next, we discuss the difference between our image evaluation method and existing image quality assessment schemes. The most common image quality assessment in novel view synthesis application is the so-called full reference method. Examples include PSNR, SSM, and LPIPS. This line of work provides accurate and detailed evaluation, but they need a pre-aligned ground truth image for a query image. Next, we have another image evaluation scheme, which is called no reference image evaluation. The examples in this line of work include NIC, PIC, and BRISC. These methods do not need a ground truth to evaluate an image, but they are limited to predefined artifacts, for example, image blur or JPEG compression artifacts. In novel view synthesis applications, there are more complex artifacts that do not belong to those predefined categories. So those no reference methods are rarely used in evaluating novel view synthesis methods such as NeRF or Gaussian splatting. Another category in image evaluation methods is so-called general reference. Examples include FID or inception scores. These methods are widely used in image generation applications to tell between real and fake images. The principle of these methods are comparing distributions between two image collections, the collection of real images and the collection of fake images. As a result, these metrics can only provide feedbacks at image set level, which is insufficient to evaluate each rendered images in a novel view synthesis application. In image and video generation applications, another line of evaluation metric is so-called multimodality image evaluation. One example in this line of work is clip score. This metric evaluates the text and image alignment rather than image rendering quality. Finally, we propose another image evaluation scheme, which uses multi-view images as reference. Our method can provide pixel-level assessment without needing ground truth images. This makes our method suitable for evaluating novel view synthesis applications. Here we would like to highlight that our cross-referencing image evaluation scheme is a brand new scheme in the existing image quality assessment landscape. In the next section, we show the performance of our image evaluation method. First, we demonstrate that our method has a high correlation with full reference scores, such as SSM and PSNR, but without requiring ground truth images. Next, we visualize CrossScore and SSM maps. On the top left, we show a query image, which is rendered from a novel view synthesis system. In the second row, we show 3 reference images at the same scene, but taken from different viewpoints. And at the last row, we show ground truth image for the query image, which we do not use during our image evaluation, but the ground truth is required to compute the SSM map for the query image. And we show that our CrossScore map is similar to SSM score map, but our method do not need a pre-aligned ground truth image. In this slide, we show an ablation study by turning reference images on and off. We demonstrate that when reference images are provided to our cross-referencing network, our method can make accurate predictions, while when we do not provide reference images, our network is essentially degraded to a monocular no-reference image evaluation method. From this experiment, we demonstrate that our method is indeed evaluating a query image by referencing other views. Here we also visualize attention weights in our cross-attention module. On the top left, we show a query image, and we also show an interest patch, which is highlighted by the magenta box. On the right, we show 3 reference images and the attention weights inside the cross-referencing module. From this visualization, we show that our method, in order to make a prediction of a query region, are paying attention to similar structures in reference images. We summarize our method in this slide. We propose a novel image evaluation scheme, which we called cross-referencing image quality assessment. This method leverages multiple views to evaluate a query image, and it does not need a ground truth image. Our method can be trained in a self-supervised manner, and our model can provide a full resolution score map for a query image. For more details, please check out our project page.